Good morning, everyone. So, thanks, Michael, for kicking this off. Thanks, everyone, for being here. Last year, I was standing here, and the talk was about Munich Quantum Software. Now I'm standing here as the CTO of the Munich Quantum Software Company. So, beginning of the year, Robert already mentioned it. We founded a startup that is dedicated to build production-grade quantum software. But I'm not only standing here as the CTO of that startup. I'm really standing here with multiple hats on, and one of them is the software company, definitely, but one of them, and a big part of it, is the chair for design automation, where I'm still a researcher, where my home is, and without the help of all these people and their great work, I wouldn't be standing up here and be able to present what I'm going to present to you in the next couple of minutes. So that's a big part of it. Big props to the team that are also running the show here. Thanks for that. Next to that, there's also the Munich Quantum Valley, without which we wouldn't have the great ecosystem we are in. We wouldn't have the best partners next doors that we could talk to, that we could reach out to, and where we could get all the interesting problems from that we get to solve with software. So let's dive right in. I hope we can all agree in this room that software is really needed across the entire spectrum of quantum, from applications all the way down to hardware, and literally everything in between. We need simulators, we need compilers, we need verifiers, we need error correction, most definitely, all of that being supported by data structures and methods, otherwise it wouldn't be scalable. And in Munich, we, together with partners from TUM and from the Leibniz Supercomputing Center, have been working on this whole big vision of the Munich Quantum Software Stack, as we call it. And I won't have the time to go into the details of all of that software stack, but what I wanted to highlight here is there's now an overview paper that you might want to check out if you want to know more about the software stack activities going on in Munich. And something that's also on this slide that I'll try to do more and more in this presentation is you see on the lower left, you see my picture in this case, but I'll always try to highlight the people that have either done the work or that are your good contact persons for reaching out to, because the event is only 2 days, and yeah, my availability is certainly limited, but there's a great number of people from our team here that you can talk to and talk about all of these topics. So within our group and within our startup, the Munich Quantum Toolkit is our baby. So it's our collection of open source toolkits and software that we've been growing over the last 5-6 years now. Some of the tools exist for even longer than that. And the list is growing and growing. So it's more and more components. It's more and more fleshed out components. I just wanted to share a couple of brief updates on what's been going on in the last couple of months in the Munich Quantum Toolkit before diving deeper. So first of all, we've had, I think, 12 releases, it says on the slide. It might have even been 13. Daniel's the one to tell. He's around somewhere, probably at the registrations desk still. We've had new releases out for basically every single tool that was on the previous slide. That was only possible because of Daniel doing phenomenal work. It allowed us to support Python 3.14, which was just released a couple of weeks back from basically day 0, which is great. If you want to use the latest version with the greatest new features, you can do this in Quantum right now, just pip install. If you don't have the Python installed, definitely check out UV. If you haven't, it's a productivity saver, so give it a try if you don't have. It also allowed us to basically support Qiskit 2.0 and also the latest versions from day 0. And the key enabler in this was really, we got so far that we set up a CI workflow that basically runs weekly on our repositories and checks out the latest Qiskit release, builds it, builds our software with it, tests it, and automatically creates an issue for us to look at when something goes wrong. We would need that for presentations, apparently. For Qiskit, this worked smoothly, and we really had 0-day support, while still trying to maintain the support for the 1.x series, because it's important for us that people, not all of the people are able to switch that early. Some of them are still stuck on old versions for reasons, for valid reasons. We still like to support this. We also just this morning crossed the 3 million download mark on our Python package downloads, which is, it's something. It's not the most important stat out there, but 3 million is still a pretty cool number. So these tools seem to be used. And we also crossed the 1.2K stars on GitHub. So people seem to enjoy the work we're doing. But that being said, I want to dive actually deeper into what the tools actually do and what we've built over the last couple of months. And we've heard a lot of interest in compilers. And you already saw that in the opening keynote, that compilers are a thing that people are interested in. And essentially, they take a quantum circuit and port it to some architecture. You see a neutral atom quantum computer on the right-hand side, and in between there is this big fat box that takes the program as an input, produces a program as an output that can run. And an important part that many people miss that still goes into there is a specification of the architecture, because the compiler needs to know what it should compile to. And this part in particular is very much overlooked in the community. Like, there is no clear standards on how to represent architectures, especially when you look to kind of different modalities. Like, there's a pretty good understanding of how to represent superconducting systems, but for neutral atoms, for trapped ions, for photonics, it really isn't that great. So that's a key obstacle that we tried to address over the last couple of months, and those that have heard me speak over the last couple of months probably have heard about QDMI by now. So it's the Quantum Device Management Interface, part of the Munich Quantum Software Stack activities, where the goal is really to get a uniform interface between the software and the hardware. And two main responsibilities there, and I'm going to talk a little bit more about one than the other. One is you take a circuit, you put it through some compiler, and then you want to execute a circuit on a certain platform, and you want to get results back. That's the one thing to standardize. But that's, to be honest, that's the more boring part. You send a circuit over, you expect certain results back. The more interesting part, especially from the compiler developer perspective, is you want to query the devices about some information. How many qubits do you have? What gates do you support? How do I compile for you? And you want to aggregate this in higher level libraries and feed that into your compiler. This is all open source. You can check out the documentation. We try to document as much as possible because, like, given that this is just an interface, we are very much aware that this needs documentation to be understood well. And this is also openly developed, so please, please, please visit the GitHub, join in, try it out. I want to give you a quick demo of how that looks like for neutral atom devices, because this is something that especially Yannick has been working on for, I'd say, months now. But let's start from the client perspective. So your client actually also being a compiler. You have your Python terminal, and you do the boring imports, as Michael called them, and then you get your device. And what you can do on that device is, of course, you can query it for its name. You can do that for every technology. But then you can also query it for its sites. Like the neutral atom device has individual sites that you need to address. And you see one specific thing, particularly for neutral atoms, you can ask the site for its coordinate, where it is located in space and time, space in this case. And for every operation the device supports, you can query the operation for its name. You can query it for more things, but those probably wouldn't fit on the slide. And what you can see here is that this is not just your regular gate list, this is also neutral atom-specific operations like load, move, and store of individual atoms. That's the more user-facing side of things. In the back, this client talks to what we call a driver that basically orchestrates many different devices. And that plugs into a device, the real representing the physical device. And on that device side, this is where the real interface lives. It's a C-based interface, so it's a bit ugly to read, but it is performant. And there's three things of interest for us right here. You can query device properties, you can query site properties, and you can query operation properties. And you feed a lot of parameters into them, and this is what the device is supposed to provide to the right-hand side in this picture. Because this is cumbersome to provide, we took it one step further, and we actually build a generator in C++ that takes a JSON file that describes your architecture, builds that into a C++ file, compiles that, and you get a shared library that you can then simply hand to your favorite HPC center that wants to run the neutral atom quantum computer and start working. If you want to check this out, this is all happening in the open. So go to GitHub, go to MQT Core. There's documentation on that. Install it. Try to work with it. That's the interface part. Coming back to the overall picture here, we typically don't consider the compiler as a black box. The end user, certainly, they should. But we, as actually software developers in Quantum, we consider this as a huge, huge box with many different tasks to be solved. And just for neutral atom computing, I'm just going to let this play. I'm not going to explain it in too much detail. All this is supposed to show is this is a really, really complicated task to go from left to right and to do this performant. To really get a performance circuit out of there that is short, that is parallelized. And if you want to know more about this line of work, first of all, talk to Yannick or Ludwig. Check out the preprint. And also, if you want to know more about other compilation techniques, like not only neutral atoms, but also superconducting systems, talk to Patrick. Ion traps, talk to Daniel and Linus. Find our people, and they'll have something to say about real hardware compilation. And if you're here next week, this paper is actually going to be presented at the ICCAT conference, which is also happening in Munich, one of the leading design automation conferences. So if you're still around or want to extend your trip, want to listen to some neutral atoms, that's your place to be. If you just want to try this out, though, that's as easy. You don't have to stay in Munich for that. It's, again, all of the compiler methods are available in our MQTQmap tool. You can just pip install that and run this in your Python console. You do the boring imports first. You define your architecture from a JSON file. You build a compiler object from that. Pretty simple so far. You import something to load your circuits. Could be your Qiskit circuit, could be QASM, could be whatever input format you want. And then you compile the circuit, and hopefully, at some point, you get code out of that. That's how easy it is. Like, it's literally, I don't know, 10 lines of Python. Might not even be that much. But code like that, like low-level code, is typically very, very, very hard to read. So what we also try to do is we make it a little bit more accessible for many different reasons. And we built a visualization tool for that. And this is really showing what a neutral atom quantum computer could be doing, picking up atoms, moving them around, applying gates, and I hope you get the idea of what's coming out of there. Not a useful computation, but an interesting illustration, I'd say. So we've built this tool not only for just the pure visualization joy, but really also for debugging the compiler. It's much easier to just load your program into there and just get good feedback of, is this compiler violating any constraints that your neutral atom device has? Or is it doing something completely stupid, and you look at it and think like, oh, yeah, that could be improved. Visualization certainly helps. This is all really open source, but just released. So the release was kicked off, I think it was midnight. Daniel did a lot of late night coding to get that release working. You can access it now. There's also documentation on this. And what you can do with that is load your video in, you get instant playback, you load in the file, and it plays. You can export that as a video. So if you want to share videos like these on conferences, you've got a tool for that now. And you can really scrub through the timeline and see where things go wrong or go right, or things might be improved. So visualization, another key point, and also a great tool for debugging. Let's take it back to this overall picture. We now talked a little bit about architecture specifications, about the compilation itself, visualizing the output. The last bit in this picture is the upper left, namely, how do we actually represent programs? How do we represent circuits? Do we even still call them circuits, or do we want to refer to them as programs now? And there's a lot to be said about this. I don't have too much time, but I'll just want to paint a brief picture of basically the landscape of intermediate representations and compiler infrastructure that evolved over the last couple of years. And there's, in my opinion, two directions. One is really quantum first. You build your infrastructure around the quantum lab, around what the quantum computer can do, and you add classical stuff on top as you need it. So basically, you start with straight line quantum programs, and whenever you need an if, a for, or whatever, you add that to your language. This is what you see with the development of OpenQASM, for example, where OpenQASM 2 was literally just straight line programs, plus an if condition that was very limited. And then you had OpenQASM 3 that extended this substantially to classical computing, to fors, if, whiles, classical computations as part of the program. You can also see this with Qiskit, which made a similar development, and you can see this in our Munich Quantum Toolkit, which was heavily inspired by these tools. We started quantum first, and whenever we needed something else, we built it on top. Now there's the second part, and if there's a quantum first, you might have guessed it, there's a classical first. You start with all the classical infrastructure that we've built over the last decades, and you add quantum on top of that. And this is a direction that has grown substantially over the last years, but especially over the last months. So all of this, or most of it, is basically building on the classical compiler infrastructure that is called LLVM. And most of you in the room hopefully have heard by now the term QIR, which stands for Quantum Intermediate Representation, which is basically an extension to LLVM that puts the quantum on top of the classical. It just defines quantum instructions, it defines how to allocate qubits, how to free them, That's more or less it. Since this is very low level, the LL stands for low level, people have looked into MLIR, which stands for multi-leveled intermediate representation, to build higher levels of abstraction and to represent programs in different dialects that you can combine with and express more structured programs. And this is a philosophy that is followed by libraries like PennyLane, or Catalyst in particular, or NVIDIA's Q2Q, and also by others that might not be explicitly building on top of MLIR, but for example, QIR's Kirin and Blockade follow a very similar philosophy, and Continuum's Hugger and Guppy also build on the same kind of ideas that go more or less classical first and adding quantum on top. Now the thing that we try to do is we try to build bridges between those two sides. So like I'll pick up on Michael's abstraction and say like we want to connect these two ecosystems together. And I'll try to show you over the next couple of minutes what we did in that direction. We did this together with people from Xanadu and tried to make PennyLane and Catalyst work with the MQT compiler. And there's one way to do it, and that is you write your program in PennyLane just as you would normally. You define your circuit. You could convert this to QASM because PennyLane supports output to QASM. We support input to QASM. So that's what you could do. You translate to QASM, and when you want to map a circuit, you go there, get your beautiful, nice program. You import that circuit from QASM to our intermediate representation. Then you define your architecture. You map the circuit. You convert it back to OpenQASM, go all the way back, and convert it back to PennyLane. That's the typical academic proof of concept, I'd say. So like, this works, but neither is it pretty nor is it performant. So we worked pretty hard to make this a little bit more performant, because what you would want, actually, is you would want to write PennyLane code and Catalyst code and just basically tag on a single line of Python to apply a certain plugin to that circuit, and what you get out of there is it's just in time compiled and you get the compiled circuit. This looks so seemingly simple, but even on that plugin alone, we spent 250 commits, and the list is still growing. So talk to Patrick a little bit about this if you want to know more details. So this was a lot of work just on that plugin alone, and next to that, we've also had over 55 issues and PRs on general MLIR support within the Munich Quantum Toolkit. So this has been quite a lot of work from quite a few people. Try to catch any of them in the venue and talk to them. Interesting field of research. I don't have too much time to go into every single detail here, but I'll try to cover at least some of what's going on behind the curtains here. And what's happening first is the input program is translated to what you see here is the MLIR program. And it's very verbose. It's not meant to be written by humans. It's actually not even meant to be read by humans that often, except for debugging reasons. But what you basically see is you do some allocations, you extract the qubits, you apply some gates, you do some measurements, and you deallocate the qubits. So nothing too fancy. And this almost looks like an OpenQASM program with different syntax. And then for optimization purposes, you translate this to a different dialect in MLIR that has value semantics, so where you can really see the information, the qubits flow from one operation to the next, and you can make connections very similar to things like you would see in a ZX diagram, for example, where you have a graph-like representation and you can traverse that graph and do optimizations much more easily on that representation. This is just the very gist of it. You typically go from this reference semantics dialect to this value semantics dialect and then back, because the way back is important for actually exporting to certain programs like OpenQASM, QIR, and so on and so forth. But that's the general idea. Now, there are certain key obstacles and challenges in all of this that we identified. So we've been working on this now with substantial manpower for like 12-ish months. So we talked about this at the last software forum already, and several key obstacles. One of them being there's a very, very steep learning curve with MLIR. It is C++ based, and it is not a particularly easy code base to get in. Like LLVM is huge. It is running our classical compilers. It has lots of requirements. It is tough to learn. Once you learned it, it gives you quite a lot, but it takes a while. Then there's the thing about versions. Like, we tried to build something that works with Catalyst. In the beginning, we were naive enough to think like, yeah, we could be using separate versions. Turns out, very hard to get that working. Even the same major version, tough to get working. Even the same minor version, tough to get working. In the very end, we had to use the same commit to get these plugins working. Now, this might be acceptable for a plugin between two players, but now add a third player and you want to be compatible with them, and yeah, it starts to get tougher and tougher. So we need solutions for that eventually. We also need to kind of figure out how to ship all of this. Like, I don't know how many of you in the room have built LLVM from source at some point. Probably not too many, I hope so. It takes upwards of 50 gigabytes of memory to actually build this. And the compiled libraries are also not particularly small. I don't want everyone in here, especially in times of shitty Wi-Fi, to have to download gigabytes of packages just to run software. So we need to find solutions for this. And two very, very important problems left. First of all, how can we move a little bit more beyond straight line programs, just programs that have quantum instruction after quantum instructions but include more structural elements, ifs, fors, while, classical computation. How can we represent these more structured programs? How can we write compilers for those? And last but not least, how can we share those compilers? How can we agree on some kind of common exchange format between compilers so that we can hopefully not re-implement the same thing 10 different times. There's been an interesting development on that in the last couple of months. I'll just highlight this here. The project is called JAF. It's kind of a collaboration between a lot of different players. Xanadu is involved, Continuum is involved, the Unitary Foundation is involved, we are, and a lot of others are involved in these discussions on trying to come up with something that could fulfill at least the last two parts in here, but maybe it also solves the version compatibility problem because we just won't have to share the same version between different tools. I have one important aspect that comes on top of all of what I've presented so far, and that is the term benchmarking. And benchmarking can mean a lot of different things. For us, coming from the software side of things and from the compiler development side of things, it typically means software tool evaluation. It means we want to have numbers in a paper that say old, new is better. That's one angle to look at it. It could also mean evaluating hardware performance, like how well is hardware performing. Things from randomized benchmarking to doing mirror circuits to computing some kind of value that says this is how good the hardware is. And last but not least, AI is literally everywhere, and you also need it for quantum. There's lots of need for data to train reinforcement learning models, for compilers, for training classifiers, for scheduling decisions, and so on and so forth. A lot of data is needed, a lot of different benchmark circuits are needed, and that's why we've built, a couple of years back, MQT Bench, and we've continued to expand it. Niels, the original author, is somewhere in the room here. I don't see him right now, but reach out to him. If you want to know more, reach out to Simon if you want to know more about the recent developments. I just want to quickly walk you through how using MQT Bench could help you with all three of those. And the first one is definitely the most common one for us, software tool evaluation. You define your circuit, and let's say you have some awesome optimizer that you want to run on your circuit and you want to benchmark. Produces a new circuit, and you want to have an end-to-end testing pipeline, so you want to test how that circuit now performs on, let's say, an IQM machine. It's these three calls. Get your benchmark, do your optimization, and again, use MQT Bench to compile that finally down to the device, and do any statistics on that circuit as you wish. As simple as that. Next use case, hardware evaluation. Let's say, boring imports first, you define your custom target for your lab architecture. And those of you who are familiar with Qiskit are familiar with that kind of code. What you can then do is you can generate a mirror circuit, for example, directly on your hardware. So you have a circuit that's basically the circuit just as regular, and then you invert the circuit, run it again, measure all qubits. Why is that an interesting benchmark? It's an interesting benchmark because you definitely know what's coming out of there. It should be all zeros, because you do all zeros, you do the computation and you completely undo the computation. It's also interesting because it's scalable. You can technically do this for hundreds of qubits, and you still have a deterministic output. The small downside, of course, is the circuit is twice as deep. So that might not be a perfect reflect of the performance of the device. But still, it's a good way to benchmark, and it's made easy by MQT Bench. Lastly, AI training. I'll keep this very short. Let's say you get a benchmark and you want to know where to run this and how to compile this. Then we've built a machine learning tool that's called the MQT Predictor that has been trained on these circuits that basically tells you, okay, you should be running on that IBM device, and it actually gives you an optimized compiler as well. This is what you get out. So that's the Python library that we developed, and we quite early realized that this is not the only way that people are using benchmark libraries. People want to be more no-code, low-code. They want to click around and hit download and just get their circuits. And the first version of this looked like that, very academic, as you probably can see. And right now is the time to launch the new thing here. And the new thing is just a completely revamp of that benchmark page that is more accessible, has more features, and hopefully also looks nicer. Huge props to Simon for actually kicking this off. Go to that new web page, check it out, play around with it, try to break it. Maybe not all of you in here right now, but the Wi-Fi is bad enough that this won't happen anyway. So I'll just demo you how using that website works. And on the one hand, you can really browse all the available benchmarks. You select your algorithms that you want. There's a couple of them, list to be extended. You select the range of qubits you want. You select the level that you want that benchmark in. You browse through thousands of benchmarks, select all of them or select just a couple of them. You download them, and you have your benchmarks. You can go ahead. Now, there's quite a few options in there. We can't generate all the benchmarks for you. So there's a second option that you can use where you can simply generate your own benchmarks. So you select whatever you want, whatever combination you want, whatever level you want, what gate set or device you want. If you want a mirror circuit, which optimization you want, and you click generate, and you'll be directed to a tracker somewhere that then shows you the results, and you can download that again. So hopefully very convenient to use. Lots of options to be added in the future. Let us know what you think about this. Try it out. And if there's something missing, then definitely give us a call. We'd like to add it. But that actually brings me almost to the close here right now. So let me wrap up about the different topics that we touched on here. So on the one hand, I briefly mentioned the Munich Quantum Software Stack efforts happening here in Munich. Big initiative, open source. If you want to know more, talk to the folks from LRC, talk to the TUM folks, talk to me. Reach out. I also talked about the Munich Quantum Toolkit, about some exciting new updates that are going on over there. Lots of exciting stuff up ahead, I can promise you that. But the majority of the talk was actually on compilers, on different aspects of compilers, and I think this is still one of the most important topics to cover here. I talked a little bit about QDMI, about our quantum device management interface and how it connects hardware and software. I talked about a little bit about neutral atoms and how to compile for these platforms, but this is really just an example of a technology that we develop compilers for. Could be neutral atoms, could be trapped ions, could be superconducting, could be photonics, you name it, we want to develop compilers for that. I talked a little bit about standards in terms of QIR and about intermediate representations like MLIR, and how we need to move from just regular circuits to something that's more called a program, more structured, less just quantum, but quantum plus classical. And last but not least, I talked a little bit about benchmarking and the important aspect that it is. Thank you for your attention. I'm open for questions.